Tēnā koutou. Welcome to this latest Environmental Research Institute seminar. My name is Charles Lee. I'm the director of the Environmental Research Institute. So I have the pleasure today to introduce Matthew Taylor, who is a PhD student in chemical engineering in the Ahuora Center for Smart Energy Systems. So Matthew is doing really interesting work on trying to decarbonize our nation's reliance on fossil fuel for processing heat. And so these are systems that consume a significant portion of the energy consumed that's burnt as fossil fuel for some of our biggest export sectors. So this work that's really relevant for a lot of people, has national relevance, and you would have noticed from the recent press releases and the ministerial visits on campus to Ahuora. So today is a great opportunity for us to learn more about what Ahuora does, and also perhaps if you're not interested in processing heat, if you're not interested in decarbonization, perhaps you'd be interested in digital twin. So, thank you.
Sweet. Let's get the slides up. Okay, so thank you for that introduction. So as you said, I'm going to be talking about sort of the role that Ahuora plays in the sort of decarbonization research space. That's going to be the first part, and then the second part is going to be my individual work within the research group. So I want to start, let's look at that title. That's quite a wordy title, all of those buzzwords that we love to hear. Let's just break it down a little bit. So we're going to start with process heat. So New Zealand's energy use is relatively substantial for the size that we are. We have a lot of transportation energy use, but we also have a large amount of industrial energy use. About a third of our total energy is industrial based. And if we have a look at where that industrial energy sort of gets distributed, most of it is through the utility systems, where utility systems represent the sort of heating and cooling requirements. If we break the utility systems down further, we actually see that more than half of our energy usage is based on fossil fuels, both through natural gas and coal. Now, as we know, we're sort of in this climate crisis at the moment based on the prevalence of fossil fuels emissions in our atmosphere. And so it's up to us now to try to decarbonize all this process heat. One of the misconceptions about industrial energy is that electricity plays a larger role than it actually does. In a processing site, about 3/4 of the energy use is actually thermal based, and only 25% of it, or in this case 28%, is electrical based. So there's a lot of energy within heat itself, not just electricity. And that's one of the things that people sort of start to neglect a little bit when thinking about all this industrial decarbonization and decarbonization in general. Within New Zealand, we have sort of a good spread of temperature ranges that our heat is applied to, where a lot of it is over 300 degrees, but also a lot of it is in that sort of 100 to 300 degrees range, and that's through the process of steam within the factories. There's a lot of steam that gets produced and a lot of steam that's needed. And that is a relatively easy area to decarbonize. Within New Zealand, pretty bad. Within New Zealand, we have a lot of processing sites, over the 200 mark, and they are spread out throughout the country. Each of these sites is different based on size and geography, and that does change their decarbonization pathways. For example, geothermal energy is heavily located in this Taupo volcanic zone, which means that sites located there can use geothermal, but everyone else can't. If we think about natural gas, the pipeline only extends in the North Island. So North Island sites can use natural gas, and if we think about in the future any biogas or hydrogen pipelines, the infrastructure is there. But for those in the South Island, they're way less, they have a lower ability to use gaseous fuels and instead sort of rely on those solid fuels or electricities. And so everybody is different, which makes the overall decarbonization project a really complex problem. And so if we have a think about decarbonization and the sort of scales that we can work on, there's multiple different scales that we can operate through. The first one is our regional and national level. This is sort of our national grid, our total energy supply. If we think about the mass balance, it's the balance around the entire islands. That's our first scale. We can then actually zoom in a little bit closer to the community level. Factories exist in communities. We see sort of the factories like Fonterra up in Tarapa. There's all these factories nestled in with other small businesses and houses. That's another subsection of decarbonisation that we can focus on. There's the site itself. How does the singular site decarbonise their process? And if we think about the site as a collection of processes, there's even individual processes. How do they get decarbonised? So us in Ahuora, we start to focus on all four of these scales. We try to help figure out the pathways to decarbonise every single aspect of New Zealand. Now, as you can imagine, because we're working at so many different scales and so many different processes, this is not that straightforward. It's a really complex problem. And part of the issue as well is that all of these scales depend on each other. They're all these sort of ramifications. You can clean your site, but maybe that increases your electrical demand of your community, which means residential electricity prices go up. There's all of these trade-offs that you have to consider, which does make it complex. If we think about the process of decarbonisation, there's this little pyramid that sort of forms all of the different steps we can do. And we sort of do it in order from bottom to top. But the first one is demand elimination. Now, this has been thrown around recently, the buzzword of deindustrialisation. We don't necessarily always want to see this. In the news recently, we've heard about the sort of Kinleith pulp mills that have been shutting down. And so demand elimination is all about stopping the unneeded processes. A site doesn't emit anything if it doesn't run. Again, that's not exactly what we want to see happen. We want to keep the productivity going. But regardless, it's still the fundamental first step. The next step that we look to is process efficiency. How do we make the individual process more efficient? Maybe that's a new type of boiler that may require less fuel for the same heat output. All of these technology changes that can affect the system. Or it could be the process pathway itself. Maybe you find a different reaction to achieve the same product, so you don't need all these extra steps. So you start to do efficiency first, and that's a common theme in decarbonisation, efficiency first. We then move on to heat recovery. Now, I know there's some thermal students in the class, this is the topic we're learning at the moment, but heat recovery is all about you have sources of heat and you have sources of cooling within a processing site. How can you link them together so you don't need all of these external utilities? And heat pumps fit in quite nicely in that area as well, because within the processing site where you have heating and cooling, they're at different temperature levels. And so heat pumps exist as technologies to change those temperature levels so you can actually make use of all the heat you have on site. Final step is fuel switching. This is sort of where I sort of put my focus in. But fuel switching, as the name suggests, is the final step. Once you've figured out all of your process, you've optimized it all, now you're just going to substitute out the coal and gas, the electricity, biomass, geothermal, whatever you want to use. Now, you'll notice that the top of that pyramid isn't sort of existing at the moment. I'm going to get rid of the clicker, that's not really doing anything. There is a final step, and that's scope 2 and 3 emissions. I'm not going to focus on scope 2 and 3 emissions for the purposes of this talk. We do cover scope 2 within Ahuora, where scope 2 is the purchasing of electricity as one of the big ones. We cover that. I'm not going to cover that today, but we're happy to talk about that later. In scope 3 emissions, they are just really hard to calculate. So for context, scope 3 emissions is all the ones about the usage of the product. So if we think about petrol car manufacturers, when the cars drive, the driver is giving off emissions, and those emissions get classified as scope 3. Hard to quantify, hard to manage. We're not going to deal with that. We're primarily focusing on scope 1. But if we are thinking about a full decarbonisation process, you need to account for them. And that really is the capstone of decarbonisation. So now let's think about how researchers approach decarbonisation. So if we think about all of these new, really advanced methods that all us researchers are putting out, they may look something like this, where we have these neural networks, these AI models, all of these fancy technologies, and they're really cool. Let's think about how industry makes their decisions. It's a lot of, oh yeah, sure, we're right. it does this in the past, I'll probably do it again. Lots of sort of judgments based on their history working with the plant. And what we sometimes find is that these aren't compatible. The tools that we produce aren't often what industry actually will end up using. It may be what they want to use, but it's not what they're actually going to implement in practice. And so there's this bit of this disconnect, which is where Ahuora is going to fit in. And part of that relates to this overall balance of money and brain power. On the left, I have the dollars that represent the costs of solutions. On the right, I have the brain that represents what we know to be the correct solution. And we have the set of scales. One of them is weighted more than the other by industry. I'm going to have a quick think. Which one do you think is going to be heavier? Which way are the scales going to tip? The unfortunate reality is that it's the money way. Industry values the economics of the project rather than what they actually know is going to work. Because at the end of the day, they have a bottom line that they've got to meet. And this is what is driving industrial decisions, and we see it all the time in our contacts with the industry. If it doesn't meet that bottom line, it's not likely to go through, even if we know it's what they should do. But one of the other aspects is that tools that we use for decarbonisation are often behind these really big paywalls, which may be licensing fees for software or anything like that. And this is another large barrier for industry that has to be overcome in order to make these solutions work. And this is where Ahuora fits in, with the energy digital twin technology. We started in 2020 with the Strategic Science Investment Fund, which was a fund that's sort of out there to help create different research groups that are actually helping deal with New Zealand's problems. There's three main objectives to Ahuora. The first one is about creating all of this new technology that's here to disrupt the market, disrupt being that sort of innovation term, but to create all these new solutions for industry to help them get across that line. We're also about growing expertise. So a lot of the students in this room are part of that expertise growth and how we can actually take our knowledge and feed it back to industry. And this wouldn't be able to be possible without the collaboration of everybody involved, both in the present now and in the future. And so our goal was to make this energy digital twin that could be sent off to sites at low cost so that they could actually start to implement it into their processes. Now, I'm going to go through our definition of a digital twin. Consider you have a process. This may be a reactor, anything like that. You have a control valve that could be automatically linked to a system and a temperature sensor. You also have your control schematics for your control system back somewhere else. There's naturally going to be linkages between the two different aspects. I have the dashed line to represent a manual data transfer. This means that somebody may be reading up an Excel sheet and then manually typing into their model what may happen, and then manually getting results out and seeing how that will change the system. We call this a digital model where there's no data transfer. Let's now pose the hypothetical. This temperature sensor, what if that was automatically linked with the digital model and could automatically change how the model acts? We now call that a digital shadow. The modeling process is shadowing behind the actual process. Now, let's say if the shadow could communicate the results back to the site, and maybe the temperature is too high, so we're going to change the feed flow by changing that control valve. This is what we call the digital twin, and this is what we have been working towards over these last 5 years. And we're doing pretty well. This is a mock-up that I took a few weeks back of what our actual platform looks like. And as you can see, there's a whole bunch of functionality that we should all be really proud of as part of the research group. We have the ability to model power flows through the system. This is your electricity-based processes, both from the source and the sink. We also have the ability for thermal processes throughout the model to actually represent what the site is doing at any given point in time. We have a whole bunch of abilities for scenarios and a lot more extra detail that I'm not going to bore everyone with, but it's really impressive coming from a chemical engineer. It's what I would have loved to have in my undergrad. this wouldn't be possible without considering all of the stakeholders that are involved in the process. There's three main stakeholder groups that are involved, and the first one is obviously us. We are part of the stakeholders because we are developers of the process. Throughout that bottom section there, you see a whole bunch of university logos. These are all different universities that we've collaborated with in the past. Now, this is not an exhaustive list. There are others beyond that, but this is just a taster of the fact that we're getting our knowledge out there, but we're also getting their knowledge to help influence our decision-making. That's the first stakeholder. The second one is the industrial sites. These are the problem owners, the ones who actually have to decarbonize. Again, this is not an exhaustive list. This is just a snippet of some of the people that we collaborate with. This way that we know that we're actually solving problems that they have, rather than making up problems that never were an issue in the first place. The final group, which sometimes may get forgotten, is the service and equipment providers. These are the consultants that are actually going to start implementing a lot of these processes. So Temperzone, they make heat pumps. Simply Energy deals with electricity contracts. Probably heard of Dieter, Becker, and Oricon as those consultants. Sometimes forgotten, but always important in this type of processing. There's a natural harmony between all three different groups, and without one of them, the whole project falls apart. So we are pretty proud that we do share amongst all of those different stakeholders. To focus on the Ahuora group as well, it's the classic photo that always gets brought up in these presentations, the people who have been part of it. Again, my common phrase, this is not an exhaustive list. There are people yet to be put on this graph, but there's been over 100 people throughout these 5 years cycling through the Ahuora project. A few thermal students, it could be more. But every single person on this graph has contributed to Ahuora in their own way. And without every single person here, the platform wouldn't be where it is. And so that's been a really big focus to help harness everybody's individual abilities and then be able to share that with the future. And this sort of leads into Ahuora's problem-driven R&D approach. It's a 6-stage process where first, you've got to identify the gaps. And this is not just for decarbonisation. This is sort of a good methodology for any type of industrial problem solving. You've obviously got to figure out what the problem is in the first place. You don't want to fall in that trap of making up problems that don't exist. From that, you can simulate some novel solutions to these problems. And this is where our chemical PhDs start to fall in, including myself. We start to simulate all these potential solutions to the problems we've identified. You create some methodologies to solve these problems. Sure, your case study may work for one side, but how does it work for every other side? Usually, as a chemical PhD student, you'd probably end it about here. But Ahuora does not end it there. This is where our software students come in. We've had a bit of a takeover by software students in recent years. And this is because of this idea of the platform. So programming all these libraries, taking the models that our chemical PhD students have learned and putting it in a digital form. Software is a big part of the platform. It naturally is the platform itself. And so creating that software that the industry wants to use, that's probably a key part of it, making it something that industry wants. You can make all this software, but if industry doesn't want to use it at the end of the day, they're not going to. Industry is stubborn, like me. And the final step of that is to train professionals for industry. This is where all those 200 students or 200 people involved in the project, this is where everybody fits in. So training everybody to take the knowledge that they've learned and share it with industry. It's very easy for academic research to fall in this ivory tower of, it's my research and I know it. Nobody else does, but I know it at least. I'm the star in my field. We don't go with that mentality. We try to make everybody have the ability to know it, which comes with a sort of easy access digital twin platform. We have 3 aims, and this is my favorite pyramid once again, but this does sort of characterize the aims that we have in our group. I'm going to start by taking away the top and bottom, because again, we don't really focus on scope 2 and 3, and demand elimination is not the ideal end goal, because that is downwards productivity. But we have these three: fuel switching, heat recovery, and efficiency aims, and these sort of summarize our distinct research groups within our massive research group. Process efficiency, as the first one on the list, if remember we're going from bottom to top, forms aim 1. Heat recovery, as that's next in line of the process, is aim 2. Fuel switching, the last step in the process, forms aim 3. That's not to say that aim 3 is the least important. I know some people in Ahuora may suggest that, but each are equally important and form this overall pyramid. But it's just the natural logical progression. So I'm going to spend some quick time to talk about the contributions of each aim. And because I'm in aim 3, that's where I'll end up talking about my work. So aim 1, process integration. We have a mock-up site where it has all of these different processes and heat exchangers. I want to draw our attention to these two heat exchangers at the top. So we have a stream here that's going from 20 degrees up to 100. We have a stream here going from 140 down to 60. Currently, they're being provided their energy through external utilities, which cost money and potentially cause emissions. Logically, we should be able to look at those temperatures and say, why don't we put them together? If this needs to cool down and this needs to heat up, well, it makes sense to marry them together and actually have them pass the heat to each other. Similarly, if we look at the bottom, we have this other stream that wants to heat up, but also a purge stream that's just going out to the environment at a high temperature. Could we match those up together? That is the fundamental principle of process integration. And it ends up looking like this, where we sort of match up these heat exchangers so we actually can reduce our overall utility use, and we do that on a large scale. This is a sort of 2 heat exchanger system. Brace yourself, we're going to go quite big here. This is what one of our students has been working on. This is a massive network of heat integration. So all of these red streams are things that need to cool down. So they start at a high temperature and they cool down to low. These blue streams are the opposite. They start at a low temperature and need to heat up. There is a natural marriage across all of these different heat exchangers based on different pathways. So these black circles and lines represent those heat exchangers that have been married up. This is process integration, and it's not as easy as I'm probably making it out to be. There's a lot of work that has to go into it, especially the automation and the optimization of it. And so this is why that is one of the founding principles of aim 1. How do we do process integration better? You may have noticed these yellow heat exchangers that are going through the system. This is the underpinning factor of aim 2, our advanced heat pump cycles. Let's talk about that real quick. There's 2 ways of supplying heat to a process. The first one is the conventional way, through boilers. Boilers typically have efficiencies below 100%, so the fuel that you put in is not equal to the fuel that you get out. There are losses along the way. They're crude technologies, but they get the job done. But if you think about the emissions profiles, using all of this extra energy, especially when it's not needed, is pretty poor. Heat pumps, on the other side, they take low-grade waste heat, which otherwise would have been useless because it's at a temperature you don't need. You charge it up with some electricity, and you get all of this energy out. So on a 100 unit of usable heat basis, boilers, you put in 120. Heat pumps, you put in just shy of 17. A massive difference, which is really great because it means that our overall energy supplies are a lot less needed. If we consider, let's do an electrode boiler instead of a coal one, you're still magnitudes different in terms of the electricity requirement. So heat pumps are really great. But they do come with their challenges. And this is why we have this research area. The main challenge is they possess a variable within their systems called the temperature lift. So you start at a low temperature and you go up to a high temperature. The bigger the difference, the worse the performance. And that can be really hard to overcome and justify when it comes to the economic analysis further down the line. As we've spent a lot of work actually working on advancing those cycles. So this diagram was made by one of our lovely students in the audience. And this is all about creating new cycles to address specific challenges within industry. This was for spray dryers within the dairy sector. This is not the only additional cycle that we've been working on. There's a lot more. There's this little timeline. This is sort of a re-timeline from that minister visit that was talked about before. We're working on building a sort of lab-scale steam-generating heat pump with our collaborators from overseas. That's our first step, because typically high-temperature steam-generating heat pumps aren't the easiest to achieve, because they often require this large temperature lift. So that's one of the things that we've been working on. Next year, right at this university, there will be an international conference on refrigerants. So for you third-year students, it may be time to actually start paying attention in class. So maybe you can attend some of these conferences. Maybe a little bit of a shout-out. I'm not the organizer, so you'd have to ask Elsa very nicely. But regardless, there's going to be this conference around refrigerants and heat pumps from all the experts across the world. A good way to disseminate a lot of this knowledge that's been built in this space, especially because New Zealand is a little bit behind when it comes to these steam-generating heat pumps compared to some of the other countries, especially in Europe. And undoubtedly, we are going to be considering future research in these new heat pump sectors, especially with steam generation. So we're going to revert back to the heat exchange network, this lovely slide again, and we're going to talk about the final set of dots on this image, the red and the blue. More specifically, we're going to end up talking about the red, but regardless, these are the utilities. You're never going to end up getting a perfect system through process integration. There's going to be some utility requirements at the end of the day. And so this is where the fuel switching aspect comes into it. How are you going to manage all of those different fuels? And again, this is where aim 3 falls in with our renewable energy provisions. So in the news, the headlines talk all the time about the current factories going from coal or gas to biomass or electrode. And this does underpin the two primary thoughts within industry. We could switch to a biomass boiler, or we could switch to an electrode boiler. Geothermal technically exists, but again, that has the geospatiality issue associated. But the common question that industry asks themselves is, should we do biomass or should we do electrode? It's a very binary decision by industry, and it's taken us a while to get to this point, but we're finally starting to actually show industry that there is merit in instead considering the question, how could we use biomass and electricity at the same time? Now, this is the underpinning focus of my personal research, and we've had some pretty good success so far, especially when it comes to changing the minds of industry. The fundamental working principle behind this system is the electricity sector, regardless of whether it's contracted or based purely on the market, has a varying electricity price. Sometimes it'll be low, sometimes it'll be high. Biomass generally has a typical contract price that you end up getting per volume of energy. So naturally, if we can make a system where when the electricity price is low, we're going to harness the electrode boiler's potential. And likewise, when the electricity price is high, we can harness the potential of biomass to offset those costs. And theoretically, this should result in a lower overall operating cost. And typically, this is what we have seen. And we call this a high-res system, so hybrid renewable energy system. We've seen a lot of adoption from industry, not necessarily actually implementing it yet, but they definitely have started baking it into their action plans. But when it comes to the research around high-res, which is becoming a big topic internationally, there's 4 key questions that have to be asked. 4 questions that everybody sort of knows, and 4 questions that underpin everybody's research, no matter what the topic. What, why, who, and how. There are 4 key questions that really can end up summarizing everybody's work. So for my one, with the high-res, we ask ourselves, what are the key inputs that go into our model? What decisions do we have to make? Our second question, why? This is a more obscure one. When it comes to optimization and decision-making with industry, why is everybody so focused on singular variables? Optimization problems often say, this is the optimal solution. Is that the best way of approaching these types of problems, to focus on one answer? This is practically, if I were to summarize this would be, who cares? Who asked? Who is using the results and why do they want to care? And finally, how can we share these results with industry in a way that's actually beneficial for them? And I have some answers. In terms of what variables we do, I can talk about this later on, but we consider all of the different parameters that go into the model. There's a lot of hidden costs that come into this type of system. One of them is the electricity infrastructure cost. And we'll see in a second that that is actually a very substantial part of how to actually get processes across the line for electrification. Infrastructure, meaning transformers, cables, anything like that, is actually almost higher than the raw electricity price itself across the entire lifetime of the system. And that is one of the reasons why lots of people have been dissuaded from doing electrical installations, because it's just too expensive. Similarly, with biomass, you have to consider the supply arrangements, but also the volume. So for typical coal sites, they may have their truckloads of volume. And generally speaking, for every 1 truck of coal, you have to have 4 trucks of biomass, which is because of the emissions of the trucks, because electric trucks aren't quite there yet. There's still a lot more volume, a lot more issues that you may have with transportation on site. Frankly, just a lot more space you have to consider. Biomass has moisture content. The water within the wood can affect your heating profile. There's a lot of complex variables that we've tried to capture within this research to get our solutions. We talked about single optimal objectives. And this graph here sort of shows that a singular optimal objective doesn't paint you the whole picture, and I don't think it ever should. This is one of the case studies that we end up doing. We have sort of operating cost on the Y, and we have a varying electrode boiler size within our high-res system. We can see it sort of forms this almost parabolic shape as it goes down. Typical optimization, if it gives you one value, will tell you you should use 6 megawatts. Whereas if we assess the entire picture, we can see that anywhere between 4 megawatts and 8 megawatts is going to give you similar operating costs, which if we think about the fact that infrastructure is such a big cost associated, for what it's worth, this bottom yellow part is the raw electricity cost. This darker yellow part is the infrastructure cost. It's more than the raw electricity. But when it comes to constraints to what's already existing in the network, understanding this wider profile actually helps us understand our stance a lot better. The who asked part is typically one of our big collaborators within this project. They are the industrial arm of Contact Power, and they are starting to implement this process into some of the sites that they're working with. So one of their big case studies that they do is Open Country Dairy, which is a dairy factory down south. They have a coal boiler and electrode boiler. Simply Energy will flick the switch, but it operates on this fundamental process. Well, based on the spot price, let's change which boiler gets used. Which technically means, it's a little bit less novel, but we're all focusing on the wider optimization profile and the general trends that we observe. But this is to say that industry is heading in this direction. And then for the how do we combine it all together? Well, if we first ask a different how question, how did I do it? It's all Python. Gecko is an optimization language. Garobi is an optimization language. It's all wibbly wobbly techno information. But in terms of how to disseminate it to industry, you may have already guessed it, but this is where Ahuora fits in with the research platform. And this is the fundamental way that we operate. A student models it, creates the methodology, supplies it to the platform. So eventually, we've had a whole bunch of PhD students in chemical. All of their individual contributions are going to end up on the platform, which is going to be great for industry as a way to actually enact some of the results that we get. Speaking of results, I'm just going to spend some time to shamelessly talk about some of mine. So I'm going to use a multi-dimensional analysis approach to talk about some of my results. One-dimensional analysis, where in this instance, we're going to fix some variables. We're going to fix boiler sizes and we're going to fix fuel prices. So I've been analyzing biomass, hybrid systems, and electrode boiler systems. And you can see this could be a typical result where the high-res is cheaper. And frankly, a lot of the time, the high-res is the cheapest option. But like I said before, with that parabolic shape, this doesn't tell you the full picture. Industry is very variable and changes all the time. So it's not fair to assume a single operating state is representative of our conditions. And so we move to a two-dimensional analysis now. Remember in that previous version, we have fixed our fuel price, we fixed our sizes, and the high-res was the cheapest. Let's propose we have a varying biomass price and a varying electricity price. Remembering that the high-res was the cheapest, if the price was about 130 and 60 on the y-axis, we can put a blue cross here, where blue represents high-res. We can then expand that. Maybe we want to model a scenario. There's a low electricity price and high biomass price. Naturally, that should favor the electrode boiler. And it does. So we represent that optimal solution with a yellow cross. I think you can see where I'm going if I'm talking about a bottom right scenario. In that case, the biomass one might be the cheapest. All of these different solutions are valid and represent different conditions. So let's combine them all together. Let's do every single possible solution, every single possible price, and see what that landscape looks like. And we can get a map that looks like this. Now, unfortunately, I did not put the contour lines in this one, but you can see that there's sections where electricity might be cheaper, or biomass might be cheaper, or a hybrid system might be cheaper. We can do the full analysis, optimizing every single possible solution. It's a bit, the optimizers in the room may hate the fact that I'm brute forcing every single possible rather than optimizing it for the best. But I think this captures a better picture of the landscape that we're working in. So naturally, the logical progression after two-dimensional analysis must be a three-dimensional analysis. And it is. So now we've got some funky cubes going on. So in this case, we're doing the same sort of thing at the bottom. We still have the electricity price and the biomass price, but now we're scaling the relative amount of biomass and an electrode boiler on that y-axis. So a 0.4 represents 40% biomass, 60% electrode boiler based on the total capital or total thermal demand. So one way to picture it is we had that map before where there was electricity in the top corner, biomass in the bottom, and then blue in the middle. We're going to take that, we're going to put it flat, we're going to do a different analysis with a different set of sizes. Take that, stack that on top. And we're going to slowly stack our way up to get this profile of our cube. And what this ends up telling us is sort of the relative risk. If we know where prices are going to end up going, we can then start to assess all of our different sizes of boilers to see where they're going to fit in. So we can start to get a picture of what the probability of a good system is going to look like. We do this to give industry confidence in what they're actually investing in, because at the end of the day, they do need a single optimal value. They can only invest in their equipment once. So they want to know they're making the right decision. And again, this sort of analysis paralysis is one of the things that can stop industry from actually implementing some of their solutions. And the curve spins around. The cube spins around. That's a little nice, fun animation. Why not? We're going to take one step backwards in dimensionality now. Technically, this is still a three-dimensional analysis, but I'm calling it 2.5D because it's still only one surface, but it's in 3 dimensions. It's 2.5. This one is a different set of scenarios where we did some consulting with industry and they wanted to know what size boiler they should use based on typical steam profiles, fuel profiles. And we end up creating this surface, again, by optimizing every single possible solution. So we have, like in this instance, we have a biomass boiler price, or biomass boiler size on this x-axis, electrode boiler size on the y, and annual cost on the z. And the whole point of this surface is we can see there's a really large, smooth, flat area. Industry doesn't necessarily have to fear about analysis paralysis because of this idea that a lot of the solutions are actually quite similar. We do generally see that in both instances, this was two different case studies, and you will have to take my word on the fact that we've done it for a lot of other prices as well and see similar results. We do see that generally a hybrid solution does end up being the global optimum. I know I said I don't like talking about global optimums, but the simple statistics tell us that the global optimums are hybrid systems. And so this is a way forward that we see going for industry, partly because it increases their security of supply as well as accounting for the prices. Everybody has a little bit of biomass and a little bit of electrode. It means that if for some reason the supply isn't there, they can still function, they can still survive. Whereas if we think about a hypothetical scenario, now I'm not trying to paint Fonterra in a bad light, just acknowledging they're a large user. If all Fonterra sites were to go biomass, how does that leave biomass for the smaller sites that cannot compete with their contracting prices? Hybrids alleviate that issue by spreading the resources out to everyone. And so we come to three overall conclusions. We have one about cost, which is sort of what I was talking about before. Hybrids are usually pretty good. We can talk about risk, talk about how this global minimum, or sort of that surface area, is pretty flat. And we can also talk about the trend that we see happening. In the processing sites, hybrid systems generally would opt for a small electrode boiler and medium to large biomass. And this almost becomes our recommendation to industry. And this is what they've been pretty receptive to. This is where a lot of industry has done their own analysis as well, much more crude than mine. But they've done their own analysis and they are coming to similar results, which is great news. It means that the work that we're doing here is actually influencing their decisions, especially when it comes to their decarbonisation pathways. So let's return back to the big picture. I'm done talking about my own individual work. Let's talk about the national system. We have all of this energy demand that must be met and all of this thermal demand that must be supplied. There's a few points that I want us all to take away from the seminar today. The first one is there's a lot of work that has to be done. It is not a simple problem to solve. There's a lot of different variables that come into it, different opinions, different personalities even within industry. But there is much work to be done, and we are trying to do that work. It is a complex problem. There is no simple fix. Every site is different. Some will use geothermal, some will use biomass, some will use electricity, some will use both, some will shut down. There's no simple solution to everything in this. No band-aid fix to get us all across the line. It is not going to be easy. There are going to be people who are going to get hurt, metaphorically, by doing decarbonisation. And it's not going to be cheap either. There's lots of expenses that are going to have to go into it. People aren't going to be happy with decarbonisation, but it must be done. But there's some good news. It is achievable. It is doable. Sure, it may not be in the projected timelines that we currently have. It may take a couple of extra years, but we will be able to get there in the end. So just to summarize the overall presentation today, some other talking points. It's cross-disciplinary as well. We've had software engineers, chemical engineers, civil engineers, electrical engineers, mechanical engineers. What other engineers do we have at Waikato? They're probably involved in our research group. Everybody has to get involved. Everybody has a stake, especially because it ends up leading to the environment and the future world we're going to live in. Everybody has a stake, so everybody should be able to contribute. We were created to make these tools for industry, to make decarbonisation cheaper and more accessible. And then a shameless one, go hybrid. I know nobody here is an industrial user that would actually apply it to, but share the news, share it to any summer placements you guys may have. Share that hybrid systems are the way to go. We put our QR code. If you want to learn more about Ahuora, feel free to scan it. It'll take you to our website. It has all the information about some of the stuff we do. Otherwise, I thank you all for your attention, and I'm happy to take any questions.
That has to be one of the most sophisticated lab presentations I've ever seen, likely from any academic. I will point out that this is being recorded and it's going to be made available online. So if an industry partner, there may be someone online right now, they can come back and view this. So, because the impact obviously potential is tremendous. Are there any questions for Matthew?
Yes.
I've got two questions. I'll ask them if there's no other questions. So it seems like to implement the model this tool as a digital twin requires infrastructural change and some of the sites to actually put forth money into changing things. Can these tools be used in the digital model, digital shadow based formats so that they could use it in that transitional period?
Oh, by all means, that is fully the intention of the platform. The intention is that, so sites have data historians that log the data of their different processes. The intention that we're aiming for, and I'm hoping a software student is not going to correct me on this, our intention is that we're going to be able to link to their historian so they can feed their own data directly into our software platform and all the models that we've created. So they can see in real time some of the effects that they could end up having to help get across the line. Because the hardest challenge with decarbonisation is the senior leadership team. And so being able to show that these results are actually applied to the specific site and in providing benefits, that's the overall goal. So yes, the digital twin should be able to be used for that type of deal. Hope that answers your question.
Yeah.
Any more questions? Excellent, because I have one on my own. I presume that when we talk about electro boilers and then biomass boilers, you're talking about boilers that directly generate heat and then feed into the system.
Yes, they create steam and then the steam gets passed.
So my question is, have you considered a possibility of a further hybrid system like a diesel electric system where you use the biomass to create steam and steam then generates electricity? Because then you only need to have one way of moving. Granted, right now the commonality is steam. The reason why I ask is because the time when you switch to biomass production of heat is also when the electricity price is high. And so if you can make use of the very fluctuations in the demand, the production demand and external demand, then you use the biomass to generate electricity, which in turn generates steam, which means you only have one boiler in theory. Yeah. Have you thought about that?
So one of the challenges with doing that type of process is the round trip efficiency and the cost of the system. Because every process that you do this type of thing introduces losses. And it's the same argument that's sort of used against hydrogen. So if you think about that type of system, you have your biomass through the boiler is not efficient. So you're losing some energy. If you were to then take that steam and run it through a turbine, turbines are also pretty inefficient. So they're both in the range of 60 to 80% efficient. So when you stack them up together, you end up losing a lot of the energy that you started with. And then when you consider the capital cost of some of these turbines, it starts to swing it not in your favor. I agree fundamentally the principle would work, but in practice, it doesn't end up working. Especially in New Zealand, when we're so far away from a lot of these manufacturers, it's a lot harder to get parts for us sometimes and a lot more expensive. So that system starts to fall apart a little bit. Kinleith was doing it a little bit for a while. Well, they are still doing it, I believe. So Kinleith does it because they have such an abundance of biomass. But for other users, unless you're a really big dairy factory, I don't see it working economically.
Is your personal research going to consider moisture content and how that affects the efficiency of biomass?
Yeah, it does factor in moisture content. It's one of the variables that we put in. And that is important to know because especially in New Zealand, different woods have different moisture contents. The South Island is going to have a lot more moisture content. Now, it's a tidbit for you thermal students. You can process your biomass pellets so that they absorb less moisture. They're called torrefied black pellets, and that sort of standardizes them. Again, that raises the cost of the system. But to answer your question, yes, I do.
Any more questions?
I got a second question. The second question is more on the adoption of this tool. Is there going to be some sort of manual or training for industry site managers, operators to then be able to use something like this?
I don't have that slide in here, but I'm glad you asked that question because the answer is yes, and we've already done it. So we have had 2 industrial training days We've had 2 industrial training days already where different representatives from industry come here, trial our software, and actually give us feedback on what they liked, what they didn't like. And they actually have a version of the platform now that they can use in their own sites now. So we have done that. In terms of a manual, I hope the software is going to write one because they put a lot of cool stuff in there. But there's a lot of complicated stuff. So surely they're going to write some documentation. I would like to hope so. No, I will say they will be writing it, and it's now on record. They will. So, but yes, there have been training days, and we continue to endeavour to train industry on this software. We're not just going to leave them out to dry.
Fantastic. Well, we don't want to drag this on because this really will be used for teaching. But we thank Matthew for his very nice presentation today.
Thank you.
Thank you. Welcome. Great. If you want to continue this discussion, you're welcome to join us because we'll have lunch with Matthew. And feel free to come along and have additional discussions. And I thank people online for attending today's seminar, and hopefully you would have learned something useful.
Should probably see if there's any questions online.
Oh yeah, this would probably be a good idea. Oh yes, there is. Good.
Oh, sorry, we didn't see your question. If you're still here, Stephanie, then feel free to unmute. I don't know if you've allowed it actually.
Oh,
yeah,
I might not have.
That was probably okay. Yeah, we didn't set it up, but let me see if we can fix that.
Or just type it out.
No, we should be able to unmute. Right, Stephanie, we've unmuted you. If you wish to,
allow you to unmute yourself.
Yeah, you can unmute yourself now if you want. Yeah, here she comes. Can you say something and we'll just see if we can hear you?
Still looks like you're muted, Stephanie.
Yeah, you're still muted.
Just type it out. It's going to be easy. Okay.
Still online.
I have a question to
You can
fill the awkwardness. Theoretically,
Yes.
if everyone implements high res, right?
Yes.
Does that mean on a national scale the electricity price will hinge?
That's a very good question. So we have had some other researchers in our group focusing on how different changes in supply and demand affect the spot price and in turn the hedging price. I will say that's out of scope for me. But we have had researchers in Ahuora focus on that very issue.
Which ones? Okay, yeah, interesting.
It might be that we just recommend that people
So
follow up with him.
So Stephanie, I think once we finish this recording, you may get kicked out of the channel. I would suggest that you go to Ahuora.
Yeah, I don't know if the emails are on there, but it's just matthew.taylor@waikato.ac.nz. So feel free to email your question there.
You want to type it in?
Yeah, I'll just type it in.